Hi all, welcome to lecture 6 on electromagnetics. This lecture is a continuation of lecture 5 and we are discussing about transmission lines itself. So we had started with transmission lines from lecture 5 and we're continuing it in this lecture. So there are three more parameters with regard to transmission lines that we need to discuss. That is input impedance, the VSWR, which is referred to as the voltage standing wave ratio, and then impedance matching. Okay, so these are actually the last three topics with regard to transmission lines. So see, we have already in lecture 5, just to review what we did in lecture 5. In lecture 5, we had derived the wave equations for voltage and current for waves which are propagating in transmission lines. And there were two main constants that we spoke about, two important constants. One is the propagation constant gamma, and the second is the characteristic impedance Z0. Okay, we had discussed about these two parameters in detail in lecture 5. So similar to characteristic impedance, another parameter, okay, that is often used in association with transmission lines is the input impedance. So we are just going to derive an expression for the input impedance of a transmission line. So for that, what we're doing is we're going to consider a transmission line which has a length L, okay, and it is characterized by gamma and Z0. So now I presume all of you know what gamma and Z0 are. Gamma is the propagation constant, Z0 is the characteristic impedance, and it is connected to a load ZL. Okay, so this is the generation side. Okay, VG is your generating voltage, ZG is the generator impedance, this side ZL is the load impedance, and this the expression that we are going to derive now, Z, that is Z in, okay, the input impedance. And we're going to derive an expression for the input impedance. So further simplifying this circuit, we're just drawing it in this way. This is the impedance of the generator, okay, and Zn is your input impedance. So first of all, what do you actually mean by input impedance is looking into the line, okay, that is here. See, looking into the line. See, this is your transmission line. These are the two conductors of the transmission line. So looking into the line, the generator sees the line with the load as an input impedance, and that is referred to as Zn. I'll just repeat that statement once again. Looking into the line, the generator sees the line with the load as an input impedance Zn. Okay. So to derive an expression for Zin, we're starting with this fact that we're assuming that your transmission line extends from Z equal to 0 to Z equal to L. So Z equal to L is the load end. Okay. See, these are the two expressions which we have derived. This is your the wave equation in voltage form, and this is the wave equation in current form, which was derived in lecture 5. So actually what is this term? This V0 plus by Z0, this denotes I0 plus, okay, that is the current wave in the forward direction. And similarly, minus V0 minus divided by Z0, this term here denotes I0 minus, which is the current flow in the negative Z direction. Okay, now so in order to find out Zin, we have to determine, the first step is V0 plus and V0 minus has to be determined. In order to determine V0 plus and V0 minus, we are going to use two end conditions. Okay. So the first end condition is this one as given here. That is, supposing what am I assuming? I'm assuming that my transmission line extends from Z equal to 0 to Z equal to L. Okay, so assuming the end Z equal to 0, Z equal to 0 is your generator end, okay, the starting point. There I am assuming that this V0 is equal to a V, a capital V, and I0 is equal to I. See now what happens, this condition I'm going to substitute into this equation. See now, when you consider the point z equal to 0, it implies that what will your gamma be? See, this is the starting point of the line. Okay, which means there is no wave propagation at that point. Okay, the starting point, I can assume that gamma is 0. So when gamma is 0, this term, e raised to term will become 1. Okay, raised to 0 means it becomes 1. So when I substitute this condition here, and if I'm just rearranging, okay, the expressions that I get for V0 plus and V0 minus are as follows. Okay, these are the expressions that I get for V0 plus and V0 minus from this equation when you substitute this condition. And further to that, now if the input impedance at the terminals, it is given by Zin, and your input voltage is V0 and the input current is I0, in that case, by voltage division rule, see, Vg stands for the generating voltage. Okay, so V0 is given by the voltage division rule, and I0 is just given by V0 divided by the total impedance in the circuit. These two equations are obtained from this figure. Okay, those two equations are obtained from this figure. So that was one condition, the first terminal condition at z equal to 0. Similarly, when I take the other end, okay, that is the z equal to L end, that means it is the load end. And there, again, I'm assuming VL, that means the load voltage is V and the load current is I. When you substitute this condition into this expression, so now this becomes e raised to gamma L. And here it is e raised to minus gamma L. Here it becomes e raised to plus gamma L. Similarly, here also. So when you substitute the end condition, the z equal to L, that condition substituted into this equation, the expression for V0 plus and V0 minus is obtained as given by equation 11.30. This is your equation. Okay. Now, what do we have to find out? We're doing all this to find out an expression for the input impedance Zn. So Zn is basically Vs by Is at any point. Okay. So what we are doing is, for this Vs and Is, okay, I'm substituting from 11.24 and 11.25. So just to go back, which is 11.24 and 11.25, these equations. Okay. And when you substitute that here, with gamma, you've assumed that your gamma is 0. Okay. So that is why that e raised to term is not present. So the voltage will be just assume if you don't have this term, what happens? Your Vs of Z is V0 plus V0 minus. And your Is of Z will be what? It will be V0 plus minus V0 minus divided by Z0. And this Z0 is just taken to the numerator. Okay, that is how you get this Zn expression over here. Okay, see, this is at the generator end. Okay, we found out this expression 11.31 at the generator end. So I can suitably assume that gamma is 0 because that is the starting point. Okay, now I'm going to substitute 11.30 into 11.31. See, 11.30 is these equations. That is your end condition, the condition at the load end. I'm going to substitute that here. Okay, and a simplification, see, this term e raised to gamma L plus e raised to minus gamma L by 2, that is substituted with cos h gamma L, and this is substituted with sin h gamma L. So tan h, we know it is sin by cos. So what happens is, see, those who are interested, you can actually substitute this equation, the V0 plus V0 minus, you substitute it here, simplify it, and if you rearrange it in this form, you will get this answer. For the others, it's sufficient. Okay, from the exam point of view, it is sufficient that you understand that substitution of this equation into this and applying this relation, it will give you this relation, Zn. So this is important. Equation 11.33, you must know. The expression for the input impedance is Z0 into ZL plus Z0 tan h gamma L divided by Z0 plus ZL tan h gamma L. Okay, and this is for the general case. The lossy case, when the line is lossless, alpha is 0 and your gamma becomes j beta. So tan h of gamma means gamma L will be j beta L. That can also be written in this way. And what happens? X0 is 0 for a lossless line. This was again explained in the previous lecture. For a lossless line, X0 is 0. There is only R0. So substituting that for a lossless line, this Z0 is actually, it can be replaced with R0. And here I'm suitably replacing this expression. So 11.33 and 11.34. So all you need to know is, okay, the basic, what do you mean by input impedance? It is the impedance as seen from the generator side when you're looking into the line and the load, that impedance is Zn. Okay, and then there are two terminal conditions that you apply to the current and wave equation, which we have already derived. So when you apply those terminal conditions and rearrange suitably, you will get the expression for Zn, and this is the input impedance. So 11.33 and 11.34 you should know. Just know those equations. Now some more terms that you need to define. See, so all these that whatever we are studying in this lecture, you just need to know the theory part. Okay, we won't be having problems on transmission lines. Normally only theory concepts are asked. So you need to know what is input impedance. Similarly, another new term is, what do you mean by the voltage reflection coefficient? So the definition of a voltage reflection coefficient is, it is the ratio at any point on the line, it is the ratio of the magnitude of the reflected voltage wave to that of incident voltage wave. Okay, and this is the notation that you use for voltage reflection coefficient. So at the load end, that is why gamma L is given. So what you understand from this is, it is the negative wave, V0 minus. So the negative wave is assumed to be the reflected voltage wave, and the positive wave is assumed to be the incident wave, and this ratio. So just know this definition and this expression. What do you mean by the voltage reflection coefficient? Okay, there are two expressions. One is this. If you're writing it in terms of the load impedance and the characteristic impedance, you can also write this as the expression for the voltage reflection coefficient. Similarly, the current reflection coefficient at any point, it is the negative of the voltage reflection coefficient. So the ratio is the same, ratio of the magnitude of the reflected current wave to that of the incident current wave. This is your current reflection ratio, current reflection coefficient, and it is equal to minus the voltage reflection coefficient. That is the relation. Okay, so these two definitions and the corresponding expressions are important. What do you mean by voltage reflection coefficient? What do you mean by current reflection coefficient? The next important term is about standing wave ratio, specifically voltage standing wave ratio. See, there is, for standing wave ratio, we have the voltage standing wave ratio, which is abbreviated as VSWR, and there is also the current standing wave ratio, ISWR. In general, SWR, the standing wave ratio, is denoted with a small s. So it can be considered to be the ratio of Vmax to Vmin or Imax to In. Okay, and the other way of writing it is 1 plus the absolute magnitude of the voltage reflection coefficient divided by 1 minus the absolute magnitude of the voltage deflection coefficient. So specifically, if you're asked to write about VSWR, that means the voltage standing ratio, then we need to consider only the definition Vmax by Vmin. Imax by In is used for ISWR. Okay, that is the current standing wave ratio. So Vmax by Vmin will give you the voltage standing wave ratio. Now what you need to understand is, normally the voltage reflection coefficient, okay, this term, it varies between 0 and 1. That is the range of variation of the voltage reflection coefficient. If the voltage reflection coefficient is 0, what happens to the voltage standing wave ratio? It will become 1. If your voltage reflection coefficient is 1, that means there is 100% reflection. The voltage standing wave ratio will become infinity. So what you need to understand is, your voltage reflection coefficient can vary between 0 and 1. And accordingly, the voltage standing wave ratio can vary between 1 to infinity. Okay, so what do you mean by 100% reflection and 0% reflection is also given. That is, see, ideally we don't prefer reflection, because if your wave gets reflected, then maximum power cannot be transferred from the generator to the load. But what we desire, we always desire that maximum power be transferred through the transmission line. So it is undesirable to have reflected waves. Okay, or any wave that is incident, it should propagate throughout and reach the load end for maximum power to be transferred from the source to the load. So this is the next term, the voltage standing wave ratio. So far we have discussed about input impedance, voltage reflection coefficient, current reflection coefficient, and the voltage standing wave ratio. And the last topic is about impedance matching. So in this last topic, you just need to know what is impedance matching, and briefly, two methods of impedance matching is very briefly explained. Okay. So impedance matching is a technique that is used to avoid reflections, ensuring that maximum power is transferred to the load impedance. So this is the voltage reflection coefficient, which we just discussed. And ideally, we prefer that for zero reflection, the voltage reflection coefficient should be 0. This condition is achieved when the load impedance is equal to the characteristic impedance. Okay, so this condition is important. So what do you mean by impedance matching? When the load impedance becomes equal to the characteristic impedance of the transmission line, then there will be no reflection and maximum power will be transferred to the load. So matching the characteristic impedance of the line to the load impedance, that is referred to as impedance matching. And why is it needed? It is needed so that maximum power can be transferred from the source to the load. And we are basically going to discuss two methods of impedance matching in transmission lines. The first method is called the quarter wave transformer matching. Okay, this is the first method. So we already know, see, if your characteristic impedance and load impedance is not equal, then your load is mismatched. There will be a reflected wave. Power transfer cannot be maximum. For maximum power transfer, what is desired? Z0, ZL should be equal and there should be no reflection. That means your standing wave ratio should be 1. So in quarter wave transformation, this matching of Z0 to ZL, it is achieved by using short sections of the transmission line. See, that is what you're going to do over here is, this is the figure. So see, this is actually the transmission line. Okay, Z0 is the characteristic impedance of this transmission line and ZL is the load impedance. In order to ensure that Z0 is equal to ZL, what we're going to do is, we're going to introduce a new section of transmission line which has a length lambda by 4. This is going to be inserted just before the load. Okay, that is this new section which has a length lambda by 4, it connects the transmission line with the load and it is an additional section. And why you are adding this, and the characteristic impedance of this new section is Z0 dash, and this is added to ensure that Z0 is equal to ZL. So the explanation is, see, the L is lambda by 4. That means the length of the new section that is added, that is lambda by 4. Okay. And so if L is lambda by 4, what happens to beta L? We know that lambda is 2 pi by beta. So beta can be written as 2 pi by lambda. L is lambda by 4. So this becomes pi by 2. So in the expression for input impedance, if you remember, this is the expression for input impedance that we derived earlier in this lecture. When it becomes tan pi by 2, this reduces to Z0 square by ZL. Okay. So you get this relation. Now what do we prefer? For impedance matching, Z0 should be equal to ZL, which means if these two should be equal, it also implies that the input impedance and the characteristic impedance of the transmission line, that should also be the same. So what is the effect? What happens is, when I add this new section here, I'm going to choose Z0 dash. Z0 dash is the characteristic impedance of this new section. It is chosen such that it is equal to square root of Z0 ZL. Okay, when such a choice is made, what happens? Your Zin and Z0 will be equal. That means these two will be equal and correspondingly Z0 ZL will also be equal. So all you need to know about quarter wave transformation is that we are inserting a new section which has a length lambda by 2 just before the load, and the characteristic impedance of this new section is set such that it is equal to root of the characteristic impedance of the transmission line into the load impedance. When this is done, okay, it ensures that the input impedance and Z0 are the same. So if the input impedance and the characteristic impedance of the transmission line is the same, it automatically implies that the characteristic impedance and the load impedance is also the same from this expression. And that is the desirable condition. Impedance matching is achieved if Z0 is equal to ZL. So that's what you're supposed to know about quarter wave transformation. Okay. Now, one small drawback of a quarter wave transformation is that it is a narrow band. It is suitable only for a narrow band. That is only for a desired frequency or a desired wavelength. This impedance matching can be achieved. So in order to overcome that drawback, we use another method. This is the second method, which is called the single stub matching method to achieve impedance matching. So that is a stub. Okay, that is again a small section which is placed parallel to the main transmission line at a suitable distance from your load end. Okay, so this is a new section. So the length of the stub is LS and it is placed at a distance L1 from the load end, from ZL. Okay, and the configuration is parallel. The stub is placed in parallel to the main transmission line. So what happens in this case? See, the load impedance is ZL, the characteristic impedance is Z0. What is our objective? No reflection should be seen by the generator. If there is no reflection, it implies that the maximum power will be transferred from the source to the load. So conceptually, what we're doing is, when you add a stub, okay, to the main line, the reflected wave from the short end of the stub, it will cancel the reflected wave from the load. That is what is happening is, when you're placing a stub parallel to your main transmission line, okay, whatever that is, if at all any reflection in the wave occurs from the load side, there is a reflection that is produced as a result of placing this stub, and those two reflections will cancel each other, which means the effect of reflection is totally cancelled out and maximum power can be transferred. And since we're using a parallel connection, okay, admittances will be used in the analysis than impedances because the connection is parallel. And there is a chart called the Smith chart. So we don't have to go into the details of the Smith chart. All you need to know is that Smith chart is a method, okay, that is used for used in the single stub matching, okay, for analysis of single stub matching to properly match the impedance. Just know that Smith chart is used. We're not going into the details. And the advantage and disadvantage of the single stub matching method when compared with quarter wave transform is mentioned. Just go through it on your own. So actually with this, I'm concluding the lecture, and our topics on transmission line also is complete as per the syllabus. So lecture 5 and lecture 6 covers all the topics in transmission lines. Mainly focus on the concepts. Okay, usually only theory questions are asked from transmission lines. So the wave equation in current and voltage, you have to study propagation constant, the characteristic impedance, the input impedance, voltage reflection coefficient, current reflection coefficient, the standing wave ratio, finally what is impedance matching, and the two methods of impedance matching. Okay. These are the main important topics that you need to study in transmission lines. So with this, I'm concluding my lecture. Thank you.